In chemistry, one of the most important quantities is called the mole. So what is a mole? Well, first of all, we need to know a little about early chemistry. And early chemistry was focused on a few things, but one of those things was whether different elements had different masses. Now, at the time, they called this atomic weight, and they did various experiments where they weighed reactants and products to work out how much mass there was in each atom, and they came up with this table. John Dalton published a table of his atomic weights, and that leads to the question: well, if we have atomic weights, then that's all well and good, but how many actual atoms or molecules or particles are there? Now, we can work this out. We can get around this by taking a ratio. So, for example, if we have water, and we have water is made up of two hydrogen atoms, each with a relative mass of 1, and an oxygen atom, which has a relative mass of 16, and therefore we end up with a relative mass of 18 in total. Okay. Now, if we want to define a certain number of particles, if we take the relative mass, 18, and say, right, okay, well, if I had a set number of those, then I could make it so that the mass is 18 grams and its relative mass is 18, and that would give me a ratio of 18 grams over 18.0 equals 1, and we can define our number of particles as that. That is a certain number of particles. Now, we don't know how many particles that is at this point, but that works for any molecule or compound or element that we can come across, because if we do the same for oxygen, we can say there are 16 relative mass for each atom of oxygen, and that gives us 32 as our relative mass. And then again, if we say, right, okay, well, if each of these particles is 32, okay, as our relative mass, then if I take 32 grams of that, divide it by the relative mass of 32.0, we will get the same number as we did when we took the 18 grams of water. And we can do that with whatever we like. We can take just a ratio of the two numbers where the mass is equal to the relative mass, and that will give us the same number of particles. So this would be 2 times 16 carbon dioxide plus 12, and that would give me, sorry, that's 12.0, gives me 44.0, and then so we take 44 grams of carbon dioxide, we end up with the same number of particles, whatever that number would be. Now, we today in our A level would define this not according to any of these, because of course you can have different isotopes of a lot of different atoms. Most elements have isotopes, but we can isolate carbon-12 reasonably easily. And if we take the mass of carbon-12, that would be 1 mole, then that would obviously be 12 grams. And so we define the number of a mole of particles as the number of particles that you would get in 12 grams of carbon-12. What is this number of particles, and how do we work it out? Well, we need to build on some work by someone called Avogadro, which is why the number is given as Avogadro's constant. And the number has been refined gradually over time. The first person to do some calculations on this idea that Avogadro had, which is basically a gas occupying the same volume at the same temperature and pressure, has the same number of particles, was someone called Loschmidt, who did some calculations and worked out the number of particles that he estimated per centimetre cubed, and that came up with a value which converted into metres cubed is around about 2.6 times 10 to the 25 particles in a cubic metre. And from that, if we know how many moles of gas there are in a cubic metre, we can then work out the number of particles in a mole, which, depending on how he did his experiments, he might have got a number reasonably close to our modern number, so 6.0 or up to 6.5 times 10 to the 23. There are other ways to do it, and one of the ways would be to use electrons. And Michael Faraday in 1834 knew that a mole of electrons, from his experiments, knew that a mole of electrons had a certain amount of charge. And when in 1910 Robert Millikan discovered the charge, or worked out the charge of an electron, we can then do, well, if a mole of electrons has this charge and one electron has this charge, we end up with a value of 6.02 times 10 to the 23, which is, if we use the modern values for these anyway, his value is possibly a little further out because we've refined technology since then. But nonetheless, there are different ways to reach this, and we get very similar answers. X-ray diffraction was invented a little bit later, so we can actually count atoms, and one of the things that is more recent in 2018 was a count of the number of silicon-28 atoms in a kilogram sphere of silicon 28 using one particular isotope, and that was done as part of the work to update the Avogadro constant. But we ended up with this definition for our A-level, which is actually our 1971 definition, which is that 12 grams of carbon-12 contains 6.02 times 10 to the 23 atoms. Okay, that's what we would define as Avogadro's number in terms of our A-level. Now, I mentioned the 2018 experiment, and actually, as of 2019, there is now a new definition of Avogadro's number, which is now 6.02214076 times 10 to the 23 exactly. And that's been calculated with a lot of other SI units that have been brought into line with physical constants, rather than using, for example, a kilogram as has been used to work out mass before, because if we can use a physical constant, it's going to be more accurate. So that's a brief history. So how do we use it? Well, we can use it in various different situations to work out the number of particles of something, and I've used the word particles there because the particles could be almost anything. They could be ions, they could be molecules, they could be atoms, they could even be something like protons or electrons. So if we look at, first of all, 1 mole of N2, I've drawn out a little space-filled model of N2. There's 2 atoms of nitrogen. Okay, so if 1 particle has 2 atoms, in 1 mole of N2, there are 6.02 times 10 to the 23 molecules of N2. Because every molecule contains 2 particles, which we call atoms, of nitrogen, then the number of atoms of N is actually twice as much as the number of molecules. So we would do 6.02 times 10 to the 23 times 2 atoms of nitrogen, and that would equal 1.2. I'm just going around to 3 significant figures here, I think. Times 10 to the 24 atoms of N. So if we have a look at the methane over here, if we had 6 moles of methane, then that would be 6 times 6.02 times 10 to the 23, 6 times the Avogadro number, which would be 3.61 times 10 to the 24 moles of CH4 molecules, which would also have 3.61 times 10 to the 24 moles of carbon atoms, because for every one molecule there's one carbon atom. And with the hydrogen, we would then have 6 times 4 times 6.02 times 10 to the 23. That would be 1.44 times 10 to the 25 hydrogen atoms. Because for every mole of these we have 6.02 times 10 to the 3 particles, and in each particle there are 4 hydrogen atoms. We don't have to stick with atoms. What if we wanted to know something like protons? Okay, let's think about protons here. So we have half a mole, or 0.5 moles of H2O, which means that we have 3.01 times 10 to the 23 molecules of water. And in each molecule of water we would have 8 protons for each oxygen, 1 proton for each hydrogen, so that would be 10 protons entirely. So that would be 3.01 times 10 to the 23 times 10, which would equal 3.01 times 10 to the 24 protons. We could do this with other particles as well. How about ions? Now, magnesium chloride is a giant ionic structure, and so you have a lattice rather than a molecule, but the principle is the same. If I have 3 moles of magnesium chloride, I will have 3 moles of magnesium and ions. So that would be 3 times 6.02 times 10 to the 23. And that would be 1.81 times 10 to the 24 Mg2 plus ions, because you'd have 1 Mg2 plus ion for every repeat unit there, and then if there's 3 moles of them, we have that many is your number in a mole, and then there's 3. With the chloride ions, we would then have 3 times 6.02 times 10 to the 23. So our Avogadro number is the number of particles we have in a mole. We have 3 moles, and then we're going to multiply that by 2 because we have 2 chlorine ions, or chloride ions rather, in our formula. So that would be 3.61 times 10 to the 24 Cl minus ions.